We are engineering a completely independent, custom e-commerce operating system from the ground up. Off-the-shelf platforms come with rigid boundaries. To own the infrastructure, we bypass those entirely in favor of a custom Next.js stack. This system supports specific operational constraints: highly interactive UI rendering, localized AI intelligence, native Bitcoin settlement, and automated global fulfillment. A prototype running on a local machine is easy. Taking that code and hardening it into a production-ready distributed system where money and physical goods change hands requires strict engineering. This diagram maps the foundation. We start with the Next.js front-end application layer, connecting to a Prisma ORM, routing data into a MySQL database. From there, we branch out, creating strict outbound connections to external APIs for a BTC Pay server and Printful. Production readiness at this scale means we stop relying on third-party plugins to provide features. Instead, we establish rigid architectural boundaries that dictate exactly how these systems interact. We enforce these boundaries across three core subsystems: the interactive front-end presentation layer, the deterministic AI logic, and the asynchronous payment and fulfillment workflows. Technical independence doesn't come from just writing custom code. It comes from owning and controlling every single layer of the infrastructure. The primary engineering challenge on the front end is interactivity. Every static product illustration must function as a paintable canvas for the user. The naive approach is to treat every piece of art as a bespoke application, assigning custom SVG regions, mapping object IDs, and attaching unique event listeners to each individual illustration. Building bespoke logic for every image fractures the code into unmanageable paths. To solve this, we pivoted to a strict layer stack. The immutable base artwork sits on the bottom. Above it, a transparent canvas slides into place. When a user selects a brush, dye, or eraser, those tools interact exclusively with the transparent overlay. The original source image is never touched. This creates a massive data advantage. We avoid saving heavy image files after every edit. Instead, interactions are recorded as lightweight data arrays, tracking coordinates, tool states, and hex codes directly on the overlay. Storing strokes as raw data completely decouples the presentation layer from the database. It keeps the front end highly performant and allows users to instantly undo or replay their actions. Building a scalable, interactive front end requires treating source assets as immutable input. The user's interaction state must exist in a completely separate layer. On the back end, the platform requires an admin intelligence layer to handle semantic search, enforce brand guidelines, and generate automated analytics summaries. The standard industry practice right now is to hook the dashboard directly into an external large language model API to process every query at runtime. This flowchart illustrates the runtime LLM model. Each user request hits an API, travels to an external LLM, and cycles back, incurring compounding costs and latency. Worse, it creates a massive privacy liability, as packets containing personal information flow completely outside the system. We eliminated this risk by enforcing a deterministic solution. We shifted all AI processing exclusively to the offline authoring and build phases. This creates what we call a retrieval-only growth library. The system's intelligence is sourced locally from established documents, rather than generated dynamically on the fly. In the deterministic model, an authoring LLM generates static embedding data exactly once, storing it permanently in a local vector database. Users query this database instantly. The loop between the request and the data is entirely closed. There are occasional edge cases where a system administrator legitimately needs the reasoning power of an external LLM for deep strategic analysis. To handle that safely, we built an export context protocol. This protocol applies rigid sanitization. It strips all customer emails, removes specific order IDs, and generates a clean markdown file. The admin can safely upload this anywhere. Moving to the commerce layer, the architecture is highly decoupled. The website UI, the Bitcoin settlement network, and Printful's fulfillment API operate completely independently. Any asynchronous distributed architecture carries an inherent timing risk because these separate systems process events at vastly different speeds. This sequence diagram maps a critical failure mode. If a payment webhook fires prematurely, it triggers the fulfillment API. If the payment ultimately fails on the blockchain, the system ships a physical good that was never paid for, resulting in an unrecoverable financial loss. The engineering fix for this race condition is strict database state gating for all asynchronous actions. We map and lock specific order statuses within the database, tracking the exact lifecycle of an invoice step by step. As seen here, it requires cryptographic validation. The Printful API remains locked. It only opens after the payment webhook signature is mathematically verified and the database explicitly registers a settled state. For the initial launch, we made a pragmatic infrastructure trade-off. We utilized a hosted BTC Pay solution rather than deploying a self-hosted virtual private server. Deferring that server maintenance to a post-profit upgrade path reduces our daily operational overhead, all without compromising the integrity of the decoupled architecture. In decentralized commerce, payment webhooks are the absolute hinge of operational safety. They must be engineered from day one as zero-trust boundaries. With the application logic solidified, the final step is the deployment infrastructure required to actually host and expose the system to the public. Local development abstractions like SQLite databases and local environment variables must be completely discarded for production. We execute a production database deployment, moving the Next.js application state to a fully managed MySQL instance using Prisma schema migrations. Then comes the invisible infrastructure work required to make the application reachable and reliable, beginning with raw DNS delegation across the hosting providers. To guarantee email deliverability, we configure strict SPF, DKIM, and DMARC records. Watch these distinct layers: front-end, data, payments, and networking, stacking and locking together. Then, automated CI/CD pipelines ensure every future deployment flows predictably into this hardened state. The integration of deterministic AI, universal presentation layers, and state-gated webhooks creates a truly sovereign operating system. True system architecture isn't about connecting a web of third-party features. It is about establishing rigid, engineered boundaries that guarantee operational independence and continuous, scalable growth.